Welcome to my channel. In this video, we are going to cover the topic called Physics of Semiconductor, Module number 4, Electrical Conductivity in Solid. Before we are going to start the video, I would like to request you to subscribe to my channel and don't forget to share with your friends and press the bell icon so that you will get first notification whenever I upload the video. With this, let's play the intro. Before we are going to start the physics of semiconductor, let us see what are the important topics we need to cover in this video. We will start from Fermi level intrinsic semiconductor, expression for concentration of electrons in conduction band, holes concentration in valence band. Only we are going to cover here is the expression which is there in as per VTU syllabus. Then conductivity of semiconductor, that is the derivation, and Hall effect, definition, and expression for Hall coefficient, derivation. So in this module or in this chapter, we need to know two important concepts. One is conductivity of semiconductor, which is derivation. You may expect this concept for 8 to 10 marks. Along with this, second one is expression for Hall coefficient. This is also you can expect for 8 to 10 marks concept. With this, let's try to understand the basic information related to semiconductor. So what is semiconductor? The material conductivity which lies between that a conductor and an insulator called semiconductor. This is the definition. Now, how you can say a material is an insulator? So in the first diagram, as you can see here, the conduction band which is completely empty, valence band which is completely filled with electron. When these two bands energy gap is more than 3 electron volt, then that material shows the insulating characteristics. That's why we call it as insulating material. Now, what is conductor? If the conductor partially filled conduction band and partially unfilled valence band is energy gap between these two are very low or merge with each other, then this material act as a conductor. That's why we call it as conducting material. Now what is semiconductor? As we can see in the definition, the material lies in between insulator and conductor. That means when there is no temperature, then this semiconducting material act as an insulating material, because the energy gap between conduction band and valency band is more, so that electron do not be able to transfer from valence band to conduction band. Due to this reason, the material act as an insulator. When we increase the temperature or impurity in these two cases, then there will be a shift in Fermi energy level. So due to that reason, this material start to react as a conductor. So in that case, what happen? The energy gap between conduction band and valence band will be reduced due to temperature or impurities. This type of material we call it as semiconducting material. After knowing what is semiconductor definition, let us see the types of semiconductor. There are two types of semiconductors are there. First one is intrinsic semiconductor or elemental semiconductor. Second one is extrinsic semiconductor or compound semiconductor. So let us see one by one. So let us see the intrinsic semiconductor definition. As we already know that the purest form of the semiconductor is nothing but intrinsic semiconductor. If we are not adding any impurities to the semiconductor material like gallium, arsenic, gallium, arsenic or silicon. These kind of purest form of semiconductor, we call it as intrinsic semiconductor. Let us see the conductivity in intrinsic semiconductor is the addition of conductivity due to electron and conductivity due to holes. This is what we denoted as sigma I. So sigma I is equals to sigma E plus sigma H. So let us see what is the Fermi level in intrinsic semiconductor. This concept you may get in semester exam for 2 marks. That means there is an definition as well as equation. So let us see the definition part. The probability of occupation energy level in valence band and conduction band is called Fermi level. Means whenever there is an absolute 0 degree temperature, then that intrinsic semiconductor act as a perfect insulator, because the energy gap between conduction band and valence band is very large. Due to this reason, this material act as an perfect insulator. However, when we increase the temperature of the material, then free electrons and holes get generated. Due to this reason, the Fermi energy level will be shifted towards or near to the conduction band. So due to this reason, there will be reduce in energy gap between conduction band and valence band. In this case, this intrinsic semiconductor act as an conducting material. And the Fermi levels in intrinsic semiconductor equation, EF is equals to EC minus EV divided by 2. Nothing but energy gap between conduction band and valence band divided by 2, Eg by 2. Let us start to understand the conductivity of semiconductor equation. This is the important concept. You can expect this question for 8 to 10 marks. So let us see what is conductivity of semiconductor derivation. As we already learned what is free electron theory. According to free electron theory, we are going to consider these electrons are free to move in the semiconductor. But in the case of intrinsic semiconductor, holes and electrons both are the responsible for the conductivity. Due to this reason, here we just consider only electrons. After that, whatever that equation we are getting for electron, that same equation will be applicable to the holes also. Okay, so let us start with the semiconducting, considering the semiconductor, and the cross sectional area of that semiconductor is A. I is the flow of charge. I is the flow of charge which is moving in this direction, and V be the velocity of the electron. Now the electrons move through the distance V in 1 second. Then the assumptions of free electron theory, the large number of free electrons flow freely through the semiconductor whose area of cross section is A. So in that case, you can see that electron is moving in this direction because the applied electric field is in this direction. Now at the same time, this intrinsic semiconductor also carries number of holes, so these electron can move in this direction in applied electric field. So by considering this concept, we are going to write down the equation charge flow per second, that is current is equals to I is equals to number of electron, charge of the electron, area swept by this electron, and velocity of the electron. This is the equation which we are getting here. Now write down current density equation, that is J is equals to I by A. So in that case, we can write it as I number of the electron, charge of the electron, area swept by the electron divided by into velocity of the electron divided by A. So A get cancelled. In that case, the J is equals to, the equation which we are getting is number of the electron, charge of the electron, velocity of the electron, which is taken by equation number 1. Now consider mobility equation, that is mu E is equals to V by E. So ಇಲ್ಲಿ ನಾವು mu E ನ substitute ಮಾಡಬೇಕು ಇಲ್ಲಿ ಈ equationದಲ್ಲಿ. For that we are going to rearrange the equation and we get V is equals to mu E into E. So just write this equation in above equation and take it as equation number 2 and substitute in equation number 1. We get J is equals to number of electron, charge of the electron, electric field, mobility of the electron. Take it as equation number 3 here. Now let us consider the Ohm's law. The Ohm's law says J is equals to sigma into E, right? So instead of writing J, we can replace this sigma into E here. In that case, we can get it sigma E is equals to number of the electron, charge of the electron, electric field, mobility of the electron. E get cancelled. Ultimately, that equation we are getting here is for electrons. So that means sigma E, conductivity due to electron, is number of the electron, charge of the electron, mobility of the electron. This is the equation which we are getting it for the electron. Now let us find out the conductivity due to holes. In that case, we can replace E to H, so that E conductivity due to holes is equals to number of holes, charge of the holes, mobility of the holes. So these are the two equations which we got it here. Now consider, as I said, the same thing we considered here. These two equations which we got for electron, this is for electron and this is for holes, because in intrinsic semiconductor sigma I is equals to sigma E plus sigma H. So sigma E is added here, sigma H is here. So just add this, and ultimately the equation which we are getting for intrinsic semiconductor is sigma I is equals to E into number of electrons, mobility of the electron, plus number of holes into mobility of the holes. This is the semiconductor equation. Now, as per the syllabus, here we are going to just mentioning the electron concentration equation and hole concentration equation for at a given temperature. So let us start with electron concentration. The definition for electron concentration is the number of electrons in the conduction band per unit volume of the material is called electron concentration, because electron will be there in the conduction band. Now per unit volume is the electron concentration, and this is the equation which we are getting here. And the next one is the number of holes concentration. The number of holes in the valence band per unit volume of the material is called hole concentration, and this is the equation. As per the VTU syllabus, we just need to mention these two equations when they ask you to write down the definition for the hole electron concentration and hole concentration for a given temperature. The Hall effect. This is a very important concept. You may expect this question or this concept for 8 to 10 minutes. Okay, so let us see the Hall effect. First, understand what is Hall effect. After that, we can derive an equation, or we can see the derivation part. Before we are going to see the derivation, I would like to request you to subscribe to my channel, share with your friends, and don't forget to press the bell icon. So let us start with Hall effect. When a conductor carrying current is placed in a transverse magnetic field, conductor carrying current is placed in a transverse magnetic field. An electric field is produced inside the conductor in a direction of normal of both current and magnetic field. This phenomenon known as the Hall effect, and the generated voltage we call it as Hall voltage. So the same definition, let us try to understand with the help of diagram. Here we need a conductor. For that, let us consider we are going to take it as N-type semiconductor. N-type semiconductor. Why? Because we have number of electrons are more, and maximum charge carriers are electron and minimum charge carriers are holes. So that's why we are going to take it as N-type semiconductor. After that, here when we apply to normal N-type semiconductor an electric current I in this direction, usually electron move in opposite direction to the applied field. Okay, this is the normal situation. But when we apply the transverse magnetic field to the N-type semiconductor, now because of magnetic field and along with this there will be a current, the Lorentz force will be applied to the surface of this side. The Lorentz force will be there and due to Fleming's left hand rule, force will be generated in upside, and that force will be applied to the each electron which is moving from this point to this point, and because of Lorentz force the electron will start to accumulate the base of the rectangular slab of the n-type semiconductor. So due to this reason negative charge will be generated here, and opposite side positive charge will be generated, because here the number of holes will be more and here the number of electrons will be more. Now when we check these two potential difference between these two plates, there will be an voltage will be generated, and that voltage we call it as Hall voltage. I hope you got to know what is Hall effect. So let us see the Hall effect and derivation part. For that we need to draw this diagram with the semiconductor. N-type semiconducting material is placed in x-axis, y-axis and z-axis, three-dimensional space. I is in this direction, okay, and W be the width of the slab, D the distance between these two plates, means positive and negative plate. And now we applied the magnetic field in this transverse direction. Now all the electrons start to accumulate in this side, so due to that reason there will be a negative charge generated and here the positive charge generated, and here there are two forces are coming into the action. One is Lorentz force, that we take it as minus magnetic field, charge of the electron and velocity of the electron, take it as equation number 1, and another force which we call it as Hall force, that is Fh is equals to minus charge of the electron and electric field. So because here we have positive charge and here negative charge, that means positive to negative Hall effect, Hall field will be generated, and we are going to take it as equation number 2. Now here we know that FL is equals to FH, so that's why we can write these two equations like this, and here minus E and minus E will be cancelled out. So EH is equals to magnetic field into velocity of the electron. Take it as equation number 3 here. Now the D is the distance between these two plates. The D is the distance between these two plates. Now EH is the electric field which is generated between these two plates, so that's why EH is equals to VH, Hall voltage divided by distance D. So D is the distance between these two plates, so we can write it as VH, this is voltage, this V is for velocity of the electron, so don't get confused. VH is equals to EH into D. So we already know what is EH, V into V. Just substitute here and we will get VH Hall voltage equals to magnetic field into velocity of the electron and distance between two surfaces. Okay, now W be the thickness of the material, and in the z direction magnetic field is introduced. Due to that reason there is also a current. So current density is equation is J is equals to I by WD. Okay, so J is nothing but NEV. So NEV, instead of writing J we can replace this to NEV, and what is number of electrons and charge of the electron is nothing but rho. So just write down rho into V is equals to 1 by WD. So just rho is taken this side, then V is equals to 1 by WD into rho. Take it as equation number 5 here. Now we already know that equation number 4 and equation number 5. Equation number 4 and equation number 5. So just substitute it like this. Here VD and VD get cancelled. So remaining equation is Hall voltage is equals to current into V divided by W into rho. Nothing but rho is equals to I into B divided by W into VH. Take it as the Hall voltage equation. This is the Hall voltage equation. Okay, now take it as equation number 7 here. Once you got Hall voltage, let us see the Hall coefficient. As we already know that EH is equals to, or we can say EH Hall field is directly proportional to J current density into magnetic field. So to remove this proportionality, we need to consider EH is equals to RH. RH is the Hall coefficient, J into B. As we already know that what is EH? EH is the EH is equals to VH divided by D. So just write down EH is equals to VH divided by D. Okay, so and we already derived what is VH, IB by WB, IB by W into rho. So VH is equals to IB by W into rho. So just substitute in this equation, EH is equals to IB W divided by W into rho divided by D. So in that case, we can write it as IB divided by W rho D. So just substitute here, and then IB divided by W rho D is equals to RH J into B. So here we know what is J. J is nothing but I by, as we can see here, I by WD. So I by WD. So write down instead of this I by WD here. Okay. So J B divided by rho equals to RH into J into B. So JB get cancelled. The ultimate Hall coefficient equation is taken as RH is equals to 1 by rho. This is the Hall coefficient equation. This is the end of the derivation, and to derive this equation you can get it for 8 to 10 marks. I hope you got to know whatever I tried to explain in this video. So please subscribe to my channel, share with your friends, and don't forget to press the bell icon. With this, I am signing off. Thank you.